Okay, so this video is a follow-up to the zero product principle video. And, well, that answers this question that you see right here in front of you. So how can we use factoring to solve quadratic equations? The way we can do that is by using the zero product principle, right? So that's what we're going to put to use here. I'm going to take each one of these quadratics, factor them into the product of two binomials, and utilize that zero product principle to very easily find what the solutions of those quadratics are. Right, so starting with this first example, and quick side note before I forget, anytime we're using factoring to solve quadratic equations, pretty much anytime you're solving quadratics ever, there are some exceptions, you're going to want to start out in standard form, right? So anyway, in case you forgot, standard form quadratic equations look like this. Ax squared plus bx plus c equals 0. Okay, so first example, unfortunately we see a is not equal to 1. That means we're going to have to do AC grouping. I'm going to make a separate video about how to utilize the area model. I just call it the Punnett square. But I'm not going to do that here. That's going to make the video run long. So 12 times negative 10, a times c, negative 120. And now we're looking for two numbers that will multiply together to give me this, or not multiply together, that will combine together to give me this negative 7. Play with some numbers, 40 and 3. Obviously, that's not going to ever give me any kind of 7. 30 and 4, 60 and 2, yada, yada, yada. You keep on trying. It's going to be pretty tough. What you'll arrive at is going to end up being 15 and 8, right? And I'm going to need the negative to be the negative 15. And that negative 15 will multiply with the 8 to give me the negative 120 and combine with the negative 8, or the positive 8 rather, to give me a negative 7, right? So let's rewrite this guy, split bx, so 12x squared minus 15x now, plus 8x minus 10, all of that equal to 0. And then we'll group, and then we'll factor GCFs from both of these terms. So on the left, we see that we're going to have 3x as our GCF, leaving me with 4x minus 5. On the right, I can factor out a positive 2, so a plus 2, leaving me also with 4x minus 5. Again, that's always a good sign that we're going the right direction with this when those two match. So that means my GCF is those two matching binomials. So I'm going to factor out that binomial they both have in common. And that's going to leave me with the 3x plus 2. Now, unfortunately, this isn't quite obvious with my zero product principle what my two solutions are going to be. I'm going to have to do like what I did over here when I set this individually equal to 0. So I'm going to have to do that for both of them. So I'm going to say 4x minus 5 equals 0, right? Because whatever makes this be 0 makes the whole thing be 0. And likewise for this other factor, 3x plus 2, set that equal to 0. Solve them both. So here on the left, I'm going to go ahead and add 5 to both sides. Divide by 4. And I've got one of my answers. Over here, subtract 2. Divide by 3. And I've got my other answer, right? So that means one solution, so x1, is 5 over 4. The other solution, we'll call it x2, is negative 2 over 3, right? And I can check my work, right, or just kind of prove to you that this is actually the case. Because if I take this and plug it back in here, I'm going to arrive at 0. And it doesn't matter what goes on over here, right? Anything times 0 is going to give me this 0. So just to prove that point, 4 times x minus 5. And I'm not even going to bother plugging in for x over here because, again, when I get a 0 in one of these factors, anything times 0 is 0. So 4 times 5 over 4, 4's cancel. We're left with just 5 minus 5, which is 0. And it doesn't matter what this 3x plus 2 is, right? Times 0, that's still just going to multiply out and give me a 0, right? So it worked in that case. So what I'm going to want to do next is prove to you that the other one also works. So this negative 2/3, if I plug it in here to this other binomial, I know is going to give me 0. So let's go ahead and check it out. So 3 times negative 2/3 plus 2. So 3's are going to cancel, leaving me with negative 2 plus 2, which is 0. And 0 times 4x minus 5. Again, doesn't matter what that 4x minus 5 is going to be. There's no point in me plugging in for this one as well, because multiplying by 0 is still going to give me that 0. Okay, so let's move on. This next example is a way simpler example just because a is equal to 1. So that means we can just fill in the blanks there when we factor it. So we're looking for the factors of c, negative 9, that will combine to give me b, this positive 8. And that is so we can fill in these blanks that we know we're going to have because a is simply equal to 1. So that's obviously going to be a positive 9 and a negative 1. 9 times negative 1 gives me this negative 9. Positive 9, negative 1 combined to give me this positive 8. Okay, and even easier, I don't need to set these individually equal to 0 because common sense tells me that the solution here is going to be negative 9 and the solution here is going to be positive 1. Right, so another thing I want to point out, you're probably wondering, well, why did you just list the solutions this time? Shouldn't you say, x1 equals negative 9, x2 equals 1? I like writing them this way labeled out just because I'm funny that way. You don't have to do that, though. You can just list them out separated by commas. Okay, third example. So we're going to have to use AC grouping here, but we also notice that these numbers are pretty giant and pretty gnarly. It'd be nice if we could make the numbers smaller. Well, 8, 24, 18, 0. 0 is divisible by anything technically. But these are all divisible by 2. So I'm going to reduce this entire equation by a factor of 2, giving me instead 4x squared plus 12x plus 9 equals 0. Now I've got smaller numbers. Now the world's a better place. We're happier. A is equal to 1, or not equal to 1 rather. So that means that I'm going to have to go ahead and do AC grouping. 4 times 9 gives me my AC. And we need to think, what are the factors of AC that combine to give us that positive 12? Pretty obvious what it's going to be. It's going to be 6 and 6, right? 6 times 6 gives me 36. 6 combines with 6 to give me this plus 12. So let's go ahead and get to factoring. Split bx into those two 6's. Group and factor. So on the left, we see that we're going to factor out a 2x. That's going to leave me with 2x plus 3. On the right, I'm going to be able to factor out a plus 3, leaving me also with 2x plus 3. And then we're going to have something pretty interesting happen. We see the GCF between these two is 2x plus 3, leaving us, again, with 2x plus 3. Okay, so that means we have the same binomial factor twice. I'll talk a little bit about what that means here in a second. So I'm going to have to set this individually equal to 0. So 2x plus 3 equals 0. Subtract 3 from both sides. Divide by 2. So we get that x is negative 3 over 2, or negative 1.5 if you like decimals. Do I really have to do that again for this one? And the answer is no. So this is a kind of sort of rare exception where a quadratic has only one solution, but not really. We see that it happens twice. This is what we would call a double root, right? It's also what we would call a perfect square. So 2x plus 3 times 2x plus 3, we can rewrite that as just 2x plus 3 all to the second power, or all squared, right? Which means we only had to solve one time. Okay, so our first instance of a double root, right? It still technically has two solutions, but I mean, we write it down on paper just as 1. But a double root, it's still 2 of them there, just repeating. Okay, thank goodness. A is equal to 1. Don't have to do AC grouping. This is going to be quick. We just have, x squared plus 6x equals negative 8. What? We should be equal to 0, right? We should be in standard form. So we're going to have to fix that. All we're going to do is add 8 to both sides. That's going to give me x squared plus 6x plus 8 equals negative 8 plus 8. Obviously, that's just 0. And we're good. Okay, so now we're just going to fill in the blanks for what we know these two binomials have to be. So what are the factors of 8 that combine to give me this positive 6, 4, and 2? And very easily, that just means my two solutions are going to be negative 4 and negative 2. Or again, so I don't confuse anyone, one solution, so x1 would be negative 4. The other solution would be negative 2. Last example. I'm not doing too bad on time. I thought this was going to take like 15 minutes, but I'm at like 11. Okay, so again, we see we're not in standard form. We're not set equal to 0. But this is an easy fix. All I'm going to do is add 2x, subtract 3, giving me 5x squared plus 2x minus 3 equals 0. And now I'm in business, right? A is not equal to 1, so I'm going to have to do AC grouping. So AC is going to be equal to negative 15. And now I can rewrite this. Splitting BX using the factors of AC that combine to give me this positive 2, which I know is just going to be positive 5 times negative 3. So that's just going to be 5x squared plus 5x minus 3x minus 3 equals 0. Group and factor. Okay, so 5x, that's just going to be x plus 1 left over. Then over here, a minus 3. That's also going to just be x plus 1 left over. GCF of x plus 1, leaving me with another factor of 5x minus 3. This guy obviously is negative 1. This guy, however, I'm going to have to do a little bit of work, set it individually equal to 0. So add 3, divide by 5, and we get our second solution. And there it is. So that does it for this video. If you have any questions over how to use factoring to solve quadratics, send me an email. Otherwise, you know where to find me. Goodbye.